So let's make an actual skybox using the cube map texture that we loaded last time. But first, I would like to take a quick look at our shaders. See, now when we have the concept of the global uniform buffer, in which we push the data just once per frame, it would make sense to have the structures shared across the shader source files, so we can easily change or add fields there and do it in a single place without touching every shader source. So in HLSL this can be achieved using the include directive, which functions pretty much the same as it's done in the C preprocessor, right? So let's create some common HLSL file and start moving our global structures there. Let's start with the vertex shader, right? We have the global here, which is exactly the same across all the three vertex shaders, so that would be the first candidate to move, right? It would be a good idea to move such a file into a separate directory so we do not mix our actual shaders and the kind of framework that we have for them, right? So here I've created a new directory in the shaders subfolder called include. You can of course call whatever you want, maybe library or something, but let's add the file there, like this, common HLSL, and just move our global structure into it, like this, right? Now we can replace the definition in the actual vertex shader with the include, right? Now, to make the HLSL compiler aware of this, we need to specify it as an argument to shader cross. See, if we run shader cross without arguments, it will show some help mentioning this include option that serves as a include directory for the HLSL sources. So let's open our build script, build Odin, find the shader cross procedure, and simply add this -i argument together with a folder name. Let's compile and see if that works. Seems to work. So let's change all of our vertex shaders. Shader, cube map, and the light shape. Now, at least two of our fragment shaders also have the global C buffer, which is exactly the same, right? We have one for the shader, which we are using for lighting, and another one for the light shape. So let's move that into common as well. Now we have the problem that we have two constant buffer registrations using the same name, and this is something that we do not want. We want only the first one to be in the vertex shaders and the second one in the fragment shaders, right? So we could do another common include file that would be a perfectly valid solution and just include different files for different stages. Or alternatively, we could also use the preprocessor macros to actually check for which stage are we compiling and just compile the first one for vertex stage and the second one for pixel stage. So that's another option, and it seems to work with shader cross as well. So that's what I'm gonna use for now. Something like this, right? If we are compiling for the vertex shader, use this C buffer define. If we are compiling for the pixel, use this one. So this is how we are gonna roll for now. And obviously we could put some common functionality here, like BRDF functions and whatnot, some utilities. So I think that's a good thing to have. Now for the skybox. The idea with the skybox is that we draw it basically behind all of our geometry, behind all our game objects, and we always draw it around the player, not depending on where the player is. So basically this model matrix doesn't make any sense, and the view matrix shouldn't really translate our skybox. It should only rotate it, right? Because it should always follow the view, kind of. So this is one way to do it. For that we would actually need to split our view projection matrix into view and projection, so we can still apply the projection, but only apply the rotation part of the view, right? So this would be one popular solution, but turns out in reality we don't even need a mesh to draw the cube map, and what we can do instead is draw a single triangle that will cover the whole screen, and even cooler, that we don't even need any vertex or index buffers for that. And I'm gonna show you how to do that. First, let's go to our game Odin, to the game state, and actually just remove the cube map mesh, because we will not be using it anymore for the skybox. Maybe we could also rename the test cube map text to like Skybox text or something. And the same with the pipeline. Rename the setup function as well. Remove the cube map mesh. Rename the texture. Rename our setup function. Rename the field being assigned. And let's remove all the vertex attributes and even the buffer binding. We can remove the whole vertex input state field. Let's maybe also rename the shaders to Skybox while we are at it. Seems good so far. Now for the drawing, let's change the pipeline name. Let's remove the model matrix pushing because we don't need it for the Skybox. And also let's remove the vertex and index buffer pushing because we will not need those. Change the texture to Skybox text and replace these draw GPU index primitives with the standard draw GPU primitives. Just 3 vertices, 1 instance, and zeros for the offsets. And finally, this drawing code should be moved after all our entities. And that is because we assume that the actual game objects will occupy most of the screen pixels, and we can only draw the Skybox where we didn't draw any of the objects. So if the Skybox will fail the depth tests, because there are objects in front that are already drawn, it can return early and not even execute the fragment shaders for it. So that should be good for performance. Now let's rename our cube map shaders to Skybox, like this, and let's take a look at the fragment shader first. So here we just get the texture coordinates and we just sample from the cube map, and we don't need to change anything else here. Now the vertex shader is the interesting one. As I said, we don't need the model matrix, let's remove that. And for the input, since we don't have any vertex buffer and we don't have any vertex attribute, we don't take a position. However, we still need to figure out the actual positions for the huge triangle that will cover our viewport, right? And for that, we need a system value that is the ID of the vertex. Remember, we used that in one of the very first videos. In HLSL, that would be just a uint vertex ID with a SV vertex ID semantics. Now we still, of course, need to output the clip position, and we need to output the texture coordinates for our fragment shaders. Now, how do we figure out the positions? Well, for clarity, let's just define the positions that we're gonna have for our triangles. Like this, right? And these are 2D coordinates in, you can say, clip space or even normalized device space. But basically, we have first vertex at the bottom left of the viewport. Then the second one is outside of the viewport to the right. And the third one is also outside of the viewport, but to the top left. So this should be a huge triangle that covers our whole viewport. Now to get our clip space position, we can simply use the vertex ID as an index into this array. Just like this, right? We are using the z coordinate of 1 because the Skybox is the furthest thing away that we draw depth-wise, so everything that is drawn before that should occlude it, right? And then the homogeneous W component is just 1. Now we don't need the world position at all here, and we use the clip space position as the output. Now, how do we get the 3D vector that will be the texture coordinate for our cube map sampling? Let's see. These textures are just a vector from a center of a imaginary cube, right? And before we had an actual cube and passed its vertex positions as those texture coordinates vectors directly, since our vertices were positioned around the center of the cube mesh. But to actually position the mesh fragments in the world, we did transform the vertex position with our model and view projection matrices into clip space, right? Now, here we directly calculate the clip space positions, because we are just drawing a full screen triangle. And what we can do now is turn those back into kind of local vectors, similar to what we had as our input before. And we do this by undoing the projection and view transformations. For that, we need to supply the inverse versions of our view and projection matrices. So let's add them here into our vertex shader globals in our common HLSL file. Something like this. inverted view matrix and inverted projection matrix. Then add them to the Odin structure for vertex globals, something like this. Now here in game render, where we push the globals, we can use the linalg inverse to calculate them from our projection and view matrices. Very simple, right? Now back to the shader. So first we unproject our clip space position into view space position by applying the inverse projection matrix. Just a normal matrix multiplication. Next, we revert the view transformation, but without the translation part, since the Skybox doesn't change position when the camera moves. For that, we can use the same thing as we did for calculating normals before, just specify the W component as 0. And we can use the view direction instead of the input position that we had before. And that should be it for the shader, so let's reiterate. We have the predefined positions for a triangle that covers the whole viewport. Out of that, we create a clip space coordinate by taking the position for the current vertex using the vertex ID. We specify 1 as a Z coordinate, so it's always behind everything we draw, and so it will fail the depth test against everything. Then we unproject this clip space position using the inverse projection matrix. Then we unapply the view transformation, but only the rotation part of it, effectively getting the direction of the view from the center of the cube to our vertex. And then we just output that. Now the final thing we need to do to make this actually work is go back to setup Skybox pipeline procedure, set the cal mode back to backface calling since our vertex order is counterclockwise as defined in the shader, and set the depth compare operation to equal. We could also set it to less or equal, but equal should work too, because we are explicitly specifying the depth value of 1, right, in the shader. And our depth buffer is also cleared with 1. So the depth test will pass for the pixels that are still at that value, and will fail where something else was drawn, right? Now we can also disable the depth writing, because there's no point in writing 1 that is equal to 1 anyway. Let's run the game. And here it is. Gorgeous, right? Some nebula, some star. Nice, seems to work. Now, if you don't like this array here, you can actually just transform the vertex ID using some bit shifts into the same numbers. So let's also do that. First let's extract that into a variable, like this. Then we can comment this out and write a math version of that. For example, like this, right? So basically we do some bit masking and then some bit shifting and then add -1 to that. So this is how it works in the JavaScript console, for example. And that should work as well in the shader. And it does. Here I added some comments explaining how this math works, but it's just basic bit manipulation. Good. Now, before I go, let's also upload a cube map from a single image like this, with this layout. So here is basically an unwrapped cube, and we have 3 rows and 4 columns. In the first row and second column, we have the top part. In the second row, we have the left side to the front side, to the right side, to the back. And in the third one on the second column, we have the bottom part. And if you print that and fold, and maybe use some sticky tape, you can get a real-world galaxy in a cube, right? Now loading it into the GPU memory is not very complicated either. We just load a single image from the disk, but we still need to upload each side separately. And we can do that using the single image pixel data by properly specifying byte offsets and pixel strides. So let's go into our GPU module again, and our new upload procedure is actually similar to both 2D upload and the multi-image cube map upload. So let's just write a new one and copy the appropriate parts from both of them. Call it something like upload cube map texture single. Yeah, maybe I should think of some less awkward names for those. Now the signature is actually exactly the same as we have for the 2D texture. We take a single pixels byte slice as well as the width and height. Here I wrote a comment for the future reader to prevent some head scratching. Then let's define some constants for the number of rows and columns. Then we calculate the size by dividing the image width by the number of columns. We can also assert that the width and height are exactly the size multiplied by the columns and rows, so we just panic if we get something that we do not expect. Next, the GPU texture creation is exactly the same as for the multi-image cube map. We now know the size, so we just pass that. The GPU transfer buffer creation and memory copying, however, are exactly like with a 2D texture because, well, it's a single image and we just upload it as a whole. Let's also add the GPU transfer release call so we don't forget it. And now, before that, we do the upload for each side, which is where things are getting interesting. So we do a loop over each side, and in Odin we can simply iterate over the enum type like this. Inside the loop we call the same upload to GPU texture procedure, and the destination here is exactly the same as for the multi-image upload. We just pass the target texture, the cube map face as the layer, and the size as the width and height and depth of 1. It's the source argument where things are a little bit different. We of course specify our transfer buffer, but in addition to that we need to calculate the offset for the first pixels of this side in our image. And this pixels per row argument. And this argument basically specifies how many pixels to advance to get the next row, right? So what will happen is that it will read the number of pixels specified by the width that we give it here, and then it will increase the starting offset by the number of pixels that we specify in this pixels per row to get the next row. And then it will repeat the procedure to read the next row of pixels, and it will do it for the number of rows that we specify as height here. Make sense? Hopefully it does. Now, in our case, pixels per row is just the whole image width, so let's take a look at this. We start with the top face, for example, and we specify the offset that points here, where it begins. It reads this whole row, so this amount of pixels, because that's the size that we give it, the width. And then it advances the offset by the whole width. And if we remember that pixels are of course laid out as a line of the values in the memory, advancing by the whole width will basically wrap around and end up on the same horizontal position for the next row. And this will of course work for all the other sides exactly the same way, like here, or from here to here, and so on, right? So let's just put width here. And with that in mind, we just need to calculate the correct offset for each side. And remember that, unlike pixels per row, this offset is in bytes, not in pixels. And let's already return the texture here to get rid of this annoying error. So first let's actually figure out the column and the row that we need to use for the given side. That would be something like this, right? If we count from 0, then for positive x, this would be the right side. The row is the second one, so row 1, and the column is the third one, so column 2. The negative x is row 1 and column 0, positive y is row 0, column 1, negative y is row 2, column 1, positive z is the front, so column 1, row 1, and the negative z is the back, so row 1 and column 3. And now we just need to calculate the linear offset in bytes for that. For readability's sake, let's add some bytes per pixel constant of value 4. So because the pixels are laid out in memory one single pixel row after another, let's calculate the size in bytes for our cube map row, which has the height of the side size, of course. And that would be just the image width multiplied by the side size multiplied by the bytes per pixel. From that we can calculate the offset to the start of the cube map row by simply multiplying the row size by our row value. So this offset will point to the first pixel in the cube map row. Now to offset to the first pixel of the column in that row, we need to add the number of bytes taken by all the pixels before the column, right? And that would be just our side size multiplied by the number of bytes per pixel multiplied by our column value. Just like this. Let's use the offset in the source structure, like this, and that should be it actually. Now let's go to the asset module, and we can copy our 2D texture loading procedure. Rename it to load cube map texture single, and change this upload texture here to upload cube map texture single, the one that we just created, right? Now we can go to our game init procedure and load our single image cube map instead of the multi-image. Actually, let's load both of them and switch between them at runtime, just to check if they look the same. For that, let's add another texture field to the game state, something like this, Skybox text single. Let's set some boolean flag to switch between them, like Skybox use multi-image or whatever. Then let's load our new texture, like this, using our new load cube map texture single procedure and passing the single cube map image to it. Let's add a checkbox to our inspector for that boolean flag we added. And finally, in the render procedure, where we binned the fragment sampler, let's use one or another based on that boolean. Something like this. Now let's run our game and check that tick in the box doesn't make any difference, because it should be the same cube map in the end, right? Yep, that seems to work. I'm ticking and nothing is changing, which is exactly what we expected. Now, just to make sure that it works at all, let's actually replace our cube map PNG with another cube map from the same asset pack. This blue one, for example, looks pretty nice. Just like this, put it in place of the old one and run the game again. And indeed, that seems to work. We can switch between different Skybox images, and they seem to work the same, even though one is multi-image and the other is just a single image laid out in a specific way. Nice. And that's the very basic of cube maps and skyboxes for you. Now, I'm not sure what I'll do next time. There are so many different topics to explore, so I have to think about it. But still, stay tuned.